Okay, so we're gonna get started. Nick has a couple announcements first, and then Vance will be speaking after.
Hey everyone,
Great.
a couple very quick things. So the first is if you're a Mathma mentor, please check your email. There's a training next week that we'd like you to go to. The other thing is the department will be hosting a course information session. That is, emails will be sent out at some point if they haven't already, but it is happening on November 3rd at 3 p.m. Basically, it's just an opportunity for you to come hear about the classes that are being offered. The faculty who are teaching them in the spring will be sort of at this event, sort of talking about whatever they're doing. And then, there'll also be students there who have taken the classes previously, things like that. So it's a really great opportunity if you're still trying to figure out like what you want to take next semester to, go to that. And then there'll be a social the following week, just to come hang out, have a good time, have pizza, all that fun stuff. So all those announcements are in the Discord. If you're not in the Math Department Discord, you should be. Send one of the board members an email if you wanted the invite link. But you also should be getting like a lot of emails about it, and we do apologize in advance for that. But yeah, anyways, so that's in a couple of weeks.
All of this communications that you have more questions, reach out to me or Nick.
Yes. So yeah. So anyways, that's about it. So I guess I'll pass it off to your speaker, Dr. Vance.
Oh, sorry, I didn't mean to get good. I was hoping you had like 30 more seconds.
I can only talk for 30 minutes.
Okay. That's right.
It's fine.
Hi. Yes, I'm Vance Blankers. So I'm teaching a course right now, and the one student who came from that course. Right now, you don't have to call me Dr. Blankers.
Okay, Vance.
Oh, that's weird. Yeah. Okay, and I'm going to talk about fractals in Minkowski space. That's where we are, Math Club, and that's today. You can tell that I compiled this today. Okay, a disclaimer to start. Everything in here is either old, like old white dudes from 2 centuries ago wrote down about it, or and that's a whole other bag of worms. But anyway, or they're relatively new joint work with myself and these 3 names: Amanda Merkley, Tristan Renfrey, and Aaron Schugert. This was actually, they were undergrads working with me when I was a grad student. This is a few years old now, but I'm thinking about it again, and I wanted an excuse to talk about it. Cool. So there's our disclaimer. They're all fantastic. I'm sure you don't know them, but if you do, great. What university? This was back at Colorado State. I think 2 of them are in grad school, and one of them is in finance. I haven't really kept up. You got it. You got it. Yep.
Oh, wait.
Yeah. No, really hard. Really hard. I don't know where to start. Yeah. Okay, so the first word in the title is fractals. So, great. Here's a quote by one of the old white dudes, Benoit Mandelbrot. I mean, we call it Mandelbrot, but it looks French, so it'd be Mandelbrot, right? But I think it's actually German, right? So I don't know how to say his name, but that's okay because he's dead. Oh, we're recording this. So here's a quote: "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. This upsets the physicists, but it gives an accurate representation of the way the world actually works." So here are some pictures of fractals. They're kind of funky and pretty. This is the famous Mandelbrot set, Mandel, his name set. This is the Sierpinski carpet, related to the Sierpinski triangle. You've heard of that, which is related to Pascal's triangle. Heard of that, which is related to, well, this is just a fractal tree. So this is an infinite binary tree. So this is a nightmare for CS majors, right? A tree search and it has infinite leaves. But here's the working definition we're going to use. So I want to think of a fractal as something, whatever it is, which is recursive and infinitely self-similar. and whose Hausdorff dimension strictly exceeds its topological dimension. So the Sierpinski carpet, for example, I want us to think all of the black dots are the things in the set, all the white dots are the things outside the set. And oh, strike that, reverse it. I want all the white ones to be in, all the black ones to be out. And if you ask the dimension of this set as a topological space, it's a bunch of points, right? So it would be dimension 0, kind of. But if you think about what it means, what dimension means, it's a very complicated notion, it turns out. And we actually can assign this what's called a Hausdorff dimension. And if this were a nice space, if it were a circle, if it was a built-in circle, it was a manifold of any kind, it would have an integer dimension. Like I am a 3-dimensional or 4-dimensional being, right? This is, I think the dimension here is 1.827. So we have fractional dimensions going on, which is a little weird. The Mandelbrot set, here everything that's black is in the set, and everything blue is out of the set. Everything that's lit up is the edge, where some of it's in, some's out, but I gotta zoom in to see it. And if you get rid of the middle, if you toss out the middle and just keep the boundary of this set, so the boundary of something 2-dimensional should be 1-dimensional, right? But it's not, it's 2-dimensional as well. So it's weird, these things are weird. And I have a picture here in a sec. So here's a zoom in. This is the Mandelbrot set. This is what people call the Mandelbrot set. And you can kind of tell if you look like here, right? It looks very similar to this chunk, but if you zoomed in on a sub-chunk of that chunk, it also looks similar. And since this is a really lame way to describe it by me waving my hands, we're gonna exit, we're gonna go to the GIF, or GIF, or whatever you prefer. Okay. So here we're zooming in on the edge of the Mandelbrot set. Woo. Oh, and it shows up again. And there it is. And then we keep zooming in. Keep zooming in. And it gets kind of trippy. This is, I mean, not that you should do drugs, but if you're going to, this is like a video. This might be a really bad trip. You never know, right? I'm just enjoying watching it. So the idea, again, is everything that's dark colored is in the set. But we're zooming in on the boundary where it's very intricate and it's very tightly wound. And as we zoom in more and more, we just get more and more. Oh, it shook at the end. That was scary. Now it's looped, right? So this is, you zoom in on deeper and deeper scales, getting down to the Planck length, and it still just looks identical to the way it was. And you might have heard something like the coastline paradox, which is that if you measure a coastline, the more you zoom in, the longer the coastline is. And it's the same thing here. If I wanted to measure the length of the edge, well, I'm zooming in to like catch all the lengths, and it's just longer and longer and longer and longer. Okay, now we pivot back to this. I gave a talk in here last year where I showed how to insert GIFs into PowerPoints, or not PowerPoints, but Beamer. And it didn't work for me. I spent like 3 hours on it today, and it didn't work. So we're gonna have to do this awkward back and forth. Okay, so there's a pretty picture, kind of nice. We're in a math club, we should use a definition, right? So it's gonna get a little mathy. But let's call f to the n the composition of f with itself n times. So if you've done any work with dynamical systems, what we're doing is we're setting up a dynamical system that we're gonna iterate over and over and over. So we'll also pick a complex number, and we'll define the function f sub c of a complex number z to be z squared plus c. So you square it and you add a constant. You square it and you add a constant. Yeah, right, it's a quadratic function. We're using complex inputs. And then we'll define the complex Mandelbrot set to be the set of values, so the set of complex values, for which there exists some bound, such that no matter how many times I iterate this function, if I multiply it times its conjugate and take this absolute value, it's bound. Right, so this is intuition. The idea is for which constants, when I add them there on the right, for which constants is the orbit of 0 bounded? So I'm always plugging in the origin to start. So, you know, my next step, it's unlocked, you got this, you just got to finalize it. But you know, the next steps, you plug in 0, you've got f of 0 is 0 squared plus c, and then the next step you're plugging in c. So your next step is going to be c squared plus c, and then you'll square that. So you'll have c to the 4th plus 2c cubed plus c squared plus c. And you calculate that over and over, and you see for which of those things are you bounded? Do you not just go off to plus or minus infinity? There's a numerical trick you can do, which is saying, okay, I want to check if this is bounded. And I want to compute this. Like, there's no analytic solution. If I hand you a random complex number, it's going to look irrational, it's going to look transcendental, it's going to look awful. But it turns out all you need to do is check if it ever gets bigger than 2, it should be absolute value. If it ever gets bigger than 2, then it diverges and your sequence blows up. If it's less than 2, it still might blow up, but so there's a numerical criterion. You can think about coding it up in, I don't know, what do we use here? MATLAB? R, Python, C++?
Definitely not R.
Definitely not R. Yeah, well, we're not stats, right? Oh, here's the picture. Okay, and oh, why did I have the picture? I was like, yeah. So what we do, the way we make this picture, this is in the complex plane, it turns out. There's an axis here, and this is the real axis. It's symmetric around the real axis. And what we do is we color everything black that is all of the C's that this condition holds. And anything that diverges, that runs away to infinity, we color it blue. And the reason we have these colors is we keep track of how many iterations it takes to escape. So this light colored stuff right on the edge, we zoom in, it's going to be some stuff on the left is going to diverge, some stuff on the right is going to converge, but right on the line, we don't quite know. And we'll use a lighter color if it takes longer before it escapes. And so, of course, for many of these, we don't actually know, but you set it to some astronomically high precision, and you say, look, after 10 million iterations, does it go away? No, then we're going to keep it in, right? There's this numerical problem. Okay, related to the Mandelbrot set are what are called Julia sets. Julia. And the definition should look very similar. So we're going to start with a polynomial, but I'm not telling you what the polynomial is, just any polynomial, your favorite polynomial. Constant functions are boring, so your favorite non-constant polynomial.
My favorite polynomial is z squared plus c.
That's a great polynomial. In fact, we should maybe keep that in our mind. Our favorite polynomial is, this is terrible chalk. Oh my gosh. It is z squared plus c. Wonderful polynomial. And we're going to define the filled Julia set associated to that polynomial with this fancy script to be the set of values for which there exists some bounds, so that when you iterate that polynomial over and over and over and over, when you compose it as many times as you want, it's bounded. This is different than the Mandelbrot definition. And the reason is because here I'm plugging in a complex number. I'm not plugging in 0. I mean, 0 is a complex, that's fine. We could plug in 0, but we're checking for all complex numbers what goes. So even if the f that I've chosen at the beginning is the same f as before the Mandelbrot set parameterized which c values don't lead to things blowing up. And this tells us that if I pick my polynomial, which complex values in general don't blow up. Subtle difference, but different. Okay. Oh, hey, not the same. But same numerical condition, they're very related. And then, okay, this is the filled Julia set. The actual Julia set is the boundary of it. I don't know why, but that's just the definition. We're going to ignore that. I'm just going to call them Julia sets regardless. These, it turns out, are also fractals. And here, again, I would insert a bunch of interesting images, but I can't. So I'm going to go to Wikipedia. Thanks, Wikipedia. So this is an animation of Julia sets. I need the arrow. So let me get back to this one. This is a Julia set. Again, coloring similarly to how we colored before. This is also a Julia set. These are for different F values. What's that?
Nothing.
This is that with different C values. Excellent question. So this is if I pick C to be golden ratio -2 plus the golden ratio -1 times I. Why not? Why not, right? And it makes this cool little spirograph thing. And it's a fractal in that if I zoomed in, it would have that same like self-similarity property. If I zoomed in enough, you can kind of tell this looks exactly like this. Only maybe spun and like you can zoom in a bit. This, okay, now this is another random, this is a real number. Neat. So it looks like very few things actually converge here, but it's kind of spirally. They make great foam backgrounds. Okay, this one has nothing. There's stuff that converges, that diverges kind of slowly, but if you zoom in, you're not going to find anything. So this is empty, but things diverge at different rates. It's cool. There's just cool pictures of this one. We're not supposed to learn anything from it. We're just like, ooh, neat. I like these. It's like this little Eastern dragon. Yeah, exactly. And one thing I do want you to notice is here, notice this is disconnected. There's no, if I'm sitting on this leaf over here, I gotta go through a couple of dark blue spots to get over here. It's not path connected, it's not connected, it's disconnected. But Eastern Dragon, this is actually connected. It's just kind of really wonky how the path goes. But it is connected. I don't know how many there are of this. Oh, that one's fun. This one looks connected, but it's secretly not. Oh, I forgot to include this image. Oh yeah. This image is really cool. This is the Mandelbrot set where if you zoom in, it's, well, we'll get there. So look at that. We'll come back to that. It's just trippy. Okay. Now it's just like, I don't know what these images are. Yeah. I mean, I would. Anyway, I want to go back to this. What's happening here is we're taking this function and we're shifting the C value around, and then we're plotting the Julia set as the C value changes. So C is a parameter, and as it moves, the Julia set changes. And I mean, it's kind of cool, right? As it moves, the Julia set does this morphing thing in this kind of smooth, continuous, trippy way.
What's the range on C? Is it a real number?
It is all throughout complex numbers. Let's see, it goes from
0. So thanks. Oh, 0 to 2 5.
You got this. You just got to finagle it.
E equals
Or
E equals IR sine A equals 0. I see.
I think it's a random path through.
It's a circle with a radius R equals 0.7885.
Hey, there it is. Perfect. So this is doing a circle in complex space of the C, and what we get is this cool.
You can kind of follow the circle too.
Yeah.
Because there's poles.
It does. It kind of reflects.
There are poles on it which
Yeah.
stay convergent.
Okay, so I mean, I could just look at this the whole time. That'd be super fun too. Let's go back to boring looking math. But keep the images in your mind. Yeah. So it turns out the Mandelbrot set is a moduli space, which is my favorite word. That's what I study. It's a moduli space. You can also call it a parameter space for Julia sets that use that function. And there's something called dichotomy theorem, which says that if you pick this function over there, then the complex number, the parameter that you've added, C, It's in the Mandelbrot set. So it does not explode off to infinity. If and only if the Julia set that's associated with it is connected. Moreover, if the Julia set's not connected, like those few examples that I pointed out, it's totally disconnected, which means there's nothing but discrete points.
Oh, that kind of makes sense because it has to be self-similar. So if it's disconnected on a large scale, it also has to be on a small scale.
Exactly. Yes. As above, so below. Yes. And you can exploit this. Oh, I'm sorry. I hate when there's a mouse. Oh, it's still there. Well, you can exploit this connection, this fact that Mandelbrot and Julia are related, to prove results. So this is, for example, how you prove that the Mandelbrot set, the boundary, has dimension 2, even though it's a boundary, so it should have dimension 1. But you can write a proof using the fact that these are connected to do this. The phrase I was told about it is you plow in the dynamical plane and you harvest in the parameter space. So you do all your work down in the Julia sets, and then you reap what you sow in the Mandelbrot set. This is also just good. This is how moduli spaces in general work, and they're super cool. So cool that people leave. But you're missing the interactable. It's the best part.
How long?
It's instant. So on the left, I have a Mandelbrot set, and on the right, it's the Julia set associated with it. And we can see when we're outside the Mandelbrot set, it's disconnected. And as we go inside, it becomes connected. And then on the boundary, it gets real funny. You can't quite tell.
This is very worth saying for.
Well, now you may leave.
Or released.
Yeah. Oh, we can still play with this. Yeah. So you can do all sorts of cool stuff. Come on here. Go too far away, you run out of stuff, right? This is my C value, real component, imaginary component. Yeah.
If you followed right along the real line, what happens?
Yeah, perfect audience, wonderful audience. It's kind of hard to do, but you'll notice I have something that's completely symmetric. It's conjugate invariant. And I think pictures are better than anything I can say here. When you come, this will actually come out in a second. This will be really important. Also notice that I saw that picture a little bit earlier because there's some self-similarity stuff going on. But anyway, if we go here, this is on the real axis, pretty far away from everything. Oop, come on, baby. No. Ah. Oh, that's pretty close. So my imaginary unit is essentially gone. And I get this shape. So it may not be obvious or easy to see, but it turns out that where these peaks are, where this where it kind of connects, where the Julia set connects like that, this essentially forms a Cantor set. So a Cantor set is also, it's a one-dimensional fractal. It's this thing where I have an infinite number of, well, actually I have a picture of it later. But, so what happens, follow the real line, everything's connected as long as you're in here, and it's symmetric, but here you start getting weird Cantor-y things. We'll talk about what a Cantor set is in a moment, but that's, it's trippy fractal stuff. And then it breaks up. But in like a nice way, right? This is the magic of a moduli space. As you move around the moduli space on the left, the objects being parameterized, the things on the right, change. And they do so in a smooth way. And the geometry of the moduli space reflects the geometry of the objects. Connectedness is a containment issue in this case. So, yeah.
If you did it the other way, where the real number was 0 and you went up across the complex line.
Let's find out. Oh, wait. What's where everything? And then I go up, that's all that is. Weird. And then, I mean, as we go out, sorry, I'm losing my real axis. Let's go to that. I mean, and then, it's less exciting, it turns out. Staying on the imaginary axis, something happens cool, but it's less exciting. And there's a reason for that, we'll see in a minute.
Like, is it true that like, if, as you like, kind of walk around, like those, it seems like those like spaces where it's bounded and those like unbounded, like kind of like move around like smoothly. Like
Yeah.
they don't like jump around or anything. They
And
all,
that is true, yep. The only non-smooth action is ripping, it's the rip and tear from leaving the Mandelbrot set.
yes.
Because you gotta go from totally connected to totally disconnected, and that's a violent process, as we can see with these whorls showing up, right? Where that's the only, and even that's done in a smooth way, right? But yeah, it's 100%. This is, I think, what we were seeing earlier was basically this, kind of doing a circle that went in and out. But yeah, it is smooth, and you can do that in a formalized way. You can actually you can put a metric on this, and then you can define what it means for this to vary smoothly, and in fact, it does. Yeah. We're gonna abandon it. It's a super fun just to like, whee. We're gonna abandon that. We're gonna go back to this. Go to interact. There was no way I was gonna put that in a PDF, so we were always host, right? Actually, so that's actually not true. I think I mentioned this before, but it's an important PSA. Adobe, which this is running in, for whatever reason, Adobe Adobe PDF Viewer. In tech, you can write JavaScript, and Adobe will execute that JavaScript without checking. So that's why you should not open random PDFs. So we actually could probably make it interactable if we wrote some JavaScript to do so. We'd have to be using JavaScript. I'd have to sit even longer than I did before trying to get these damn diffs to work. But we could do it, and just be careful with PDFs, that's the point. Or don't use Adobe, also. Okay, great. So this is the classic story. This is old French and German folks figured this out. But there's a lot more stuff I have not said about these spaces. It's fascinating. The more the subject itself is fractal. The more you learn, the more interesting it gets. But what my group did a couple years ago was we went to Minkowski space. We went in the hyperbolic time chamber to something called Minkowski space. So what is Minkowski space? Well, we need to start with something called the hyperbolic numbers. These have a bunch of names, also called motor variables, split complex numbers, Lorentz numbers, and a bunch of other names. I think there's like 13 on one of the wiki pages. And they're a variation on a theme. So as a ring, we've hopefully learned that if you take some ring theory, you'll learn that you can realize the complex numbers as the reals adjoin a variable and then quotient out by the root of -1. Or, i.e., you take R and you give yourself a square root of -1, and then you have C. Right? So C is a two-dimensional vector space over the reals. It looks like two copies of the reals. We just give an imaginary number as well. Terrible name, should be called an incredible number, but whatever. We give ourselves I. Instead of that, we're going to take and make a space H, same process algebraically. If you don't know what these ring things mean, don't worry about them. It's totally okay. What happens is, instead of giving ourselves a square root of -1, we'll give ourselves a square root of 1. Yeah? But we don't identify it, we'll call it tau. We don't identify it with plus or -1. So 1 and tau both square to 1. In fact, so does -1 and so does -tau. They all square to 1, but they're not the same. Kind of weird. Yeah? This is still a two-dimensional vector space over the reals. And then we sometimes write H, you know, you write C as R squared. We write H as R11. We'll see why in a second. H, when we write it as R11, that's Minkowski space. Physicists care about this because R31 is how general relativity works, or what space it considers working on. Right? All of our real dimensions that we work in, the 3 dimensions that we're used to, I can move forward and I can move backwards carefully. And I can move left, right, up, down, it's all free. It's easy. You can only move forward in time. So there's 3 plus 1 dimensions, it's not 4, there's 3 plus 1. The 1 is weird, it's different. And that's Minkowski space. Okay, but much of what we've done with complex numbers when we learn those kind of still works. So for example, you can still write any hyperbolic number as a real part plus an Taoian part. I don't want to call it imaginary, right? Taoish part. There's also a hyperbolic conjugate. So you know there's a complex conjugate, which is this exact same thing, except you change tau to I. But you can do it with hyperbolic numbers too. In fact, you can do Euler's identity, except you have to use the hyperbolic versions of cosine and sine. So if you ever thought to yourself, why the hell do I care about hyperbolic sine and cosine? Here's a dumb reason to care about them. If you do something contrived, like invent this extra square root of 1, here you go. This is fine. The unit hyperbola, in fact, all 4 of them, are the new unit circle. Well, the next picture will show you that. We'll get there in a second. We can encode things using matrices. And then, so this one's for the folks who know how to deal with writing complex things as matrices and learning about Mobius transformations. You can do stuff like there. If you don't like any of that, it's okay. There's also something called a quadratic form. That quadratic form in complex world is called a metric, right? And you would, or like an absolute value. And here you can still do that. It's still the number times its conjugate. If you were in complex land, if you're trying to find the size of a number, the distance between 2 numbers, you'd have the x thing squared plus the y thing squared, but we're hyperbolic. So we have a minus. And we could write this out, but actually we don't need to, right? Just here's that number, x plus tau y. Actually, let's do it in real time. X plus tau y times its conjugate, x minus tau y. Well, this is x squared minus tau squared y squared, but tau squared had exactly 1 property, which is that it squares to 1. Cool, so do that. It's not a metric. Obviously, things can have negative size. Not a metric. And for you folks who like ring theory, C is a field, which means everything that's not 0 has an inverse, right? You can divide by anything that's not 0. Not true here. Anything on the diagonal doesn't have an inverse. You can't divide by it. It has 0 divisors. So this is not a field. It's objectively worse than complex numbers, or objectively more interesting. Your choice. Yeah.
So does that mean that the calculus is not as nice? We don't have.
Yeah. Yeah. In fact, here's an example. Here's the unit circle. This is why it's called hyperbolic numbers. So everything in red is exactly size 1. All of these hyperbolic numbers, so this is the tau axis, the real axis. All of the numbers in red have hyperbolic size plus or minus 1. It's kind of trippy. Yeah.
So this is the size, but that's not a metric.
Right.
Can we define a metric, or is that
No.
possible?
Can't, because for a lot of reasons, but maybe just the 0 divisors. Yeah.
You'll answer this later, but what happens if you combine Taoian and complex space?
Oh God. Actually, then you get R31. So In the same way, what the physicists do for general relativity is they use a space called R31, and their metrics, the way they measure distances, look like x1 squared plus x2 squared plus x3 squared minus x4 squared. And we're just using the last two. But if you throw in the complex numbers, you get these other two again. So great question. And it turns out that's why you actually would even think about doing this, is because you really want to do this when you're doing like light cones and general relativity and all that nonsense, right? But we're going to cut out, what we essentially do is say, screw these 2 dimensions. We're just going to stick with the plane, hyperbolic plane. Okay, and it turns out that, coordinate systems are flexible. They're choices we make. This is the x-axis, the y-axis. It's not really that helpful because if I'm in my usual r squared, things around here are like setting something equal to 0. And similarly, this is like setting something equal to 0, like setting x equal to 0, setting y equal to 0. But the things that don't have inverses, the things that are kind of act like 0, are on the diagonal, as the previous slide claimed. So it turns out those are kind of the right coordinates to use. You tilt your head 45 degrees, and now you have a new axis system. This is all gobbledygook, who cares? Doesn't matter. But since we can add and multiply, and since I never needed to divide when talking about Mandelbrot sets, Julia sets, we can also construct Mandelbrot sets over the hyperbolic numbers in the exact same way. So this is the exact same definition as before. I've just forced my C to be a hyperbolic number. So it has this tau component. So it's the same idea, but also note this is no longer an actual metric. This could be a negative number. Yeah. So you have to be a little careful now. We don't actually have a metric. And the meaning of multiplication is a little different because tau squares to 1. So things are a little funky. But we can also define Julia sets the exact same way. I'm not going to read it. It's the same thing. We check which numbers go off to infinity and which don't. Blah, blah, blah. Okay. So now we can ask some questions. What do these sets look like? What does hyperbolic Mandelbrot look like? Can we compute them? Like, is it feasible, like we could for the Mandelbrot set, with a computer to compute what it looks like? Is it fractal? Is the Mandelbrot fractal? Are the Julia sets fractal? If anything is fractal, look, fractal, what's its Hausdorff dimension? That's not something we're going to talk about because that's very complicated. But the thing that I was excited about was the moduli space aspect. The Mandelbrot set should parameterize the Julia sets. And then can we prove something analogous to the dichotomy theorem, which was the as above, so below, right? As you moved in and out of the Mandelbrot set, you got disconnected or connected Julias. Oh, answers. What do the sets look like? We're going to show you in a minute. Can we compute them? Yes, because I'm going to show you in a minute. Is the Mandelbrot set fractal? Maybe arguably yes in the dumbest possible way. So no. And are the Julias fractal? Yes, in a not dumb way. If anything is fractal, great. What is the Hausdorff dimension? I don't know. We didn't get that far. Our paper just says, great, future work. Okay. Is this thing a moduli space parameterizing the connectedness of Julia sets? The answer is yes, with a small caveat. So yes, if you whisper. And then can we prove a theorem analogous to the dichotomy theorem? Yes. So now let's see all that. Okay, here's the theorem. So you don't have to worry about what this says other than there's a square and there's some diagonals. Yeah, so this is a specific square. It's a really weird way of writing a square, but it's a square. And then the diagonals are the two diagonals. Yeah. The Mandelbrot set is the square union the diagonals. diagonals suck. And they're really only there because we defined things the way we did and because they're zero divisors. Because they have no multiplicative inverse, they never diverge. They kind of absorb everything into them. And so we're going to kind of ignore the diagonals. But here's the picture. Here's the Mandelbrot set over the hyperbolic numbers. You might notice it's significantly less interesting than over the complex numbers. This is the origin, by the way, where these diagonals are also in here, but this is the origin. This is the Mandelbrot set. It's lit up here. It shouldn't be. It's just an artifact of computation. It's literally just this blue square and the diagonals. Technically, I guess that's fractal because if you zoom in, it keeps looking like a blue square. Super boring, but that's the answer. Yeah.
Recognize that album cover.
Yeah, this would be a great album cover.
Guarantee it's something similar, probably is.
It could be. I hope so. I wrote a proof. None of us care. There is some cool stuff. It turns out. So one thing I will note, or I'll mention. You'll see I'm taking the hyperbolic Mandelbrot set intersecting with the real axis, which is why I was really excited. Someone asked about that. And that's actually the exact same as when I intersect the Mandelbrot set with the real axis. So it turns out, we go back to this picture. So this is the real axis. It's right. It splits the, it's a diagonal of the square. And it turns out, this is exactly the same place the Mandelbrot set intersects the real axis. So the Mandelbrot set has the small loop and then the big loop, and then it kind of goes off. So this is the exact same real points as the Mandelbrot set, the classic. I just want to highlight that. Okay. And then, oh yeah, that's a good title. So we have the dichotomy theorem, which said there's two things. If you have a point, if your C value is in the Mandelbrot set, Julia was connected. If the point was outside the Mandelbrot set, Julia was totally disconnected. That was the dichotomy theorem. We have a quadchotomy theorem. It's not a word. Actually, it's in the published article, so it's now a word. That's how this works, right? Because there are four things that can happen. Okay, this is the setup. This is just the exact same statement as before, basically. Here are the four things that can happen. Well, if C is inside the square, so it's inside the Mandelbrot set, then the Julia set is connected. So that is still true. That was exactly the same case in the complex world. If it's above or below or to the side, this side of the square, then the Julia set, but the other one is in, like one is out and one is in, like you're in kind of I'll have pictures in a second. If you're outside the Mandelbrot set, but in a nice tight way, your Julia set is disconnected, but not totally disconnected. If both of them are way off in the middle of nowhere, the Julia set is totally disconnected. And sometimes the Julia set's just totally empty. So let me show you all the pictures for this. Oh, and we can specify what it looks like. Here we go. Okay. Here's the Mandelbrot set. If I am sitting over here, hanging out, this is what my Julia set looks like. It looks like a Cantor set that's got stretched out. If I'm way over here, my Julia set is empty. Nothing said. Technically, this is fractal, right? But in a really boring way. If I am up there, oh no, sorry. If I'm in the Mandelbrot set, everything's symmetric over the axis. If I'm in the Mandelbrot set, my Julia set looks like a rectangle. Also, again, boring. And if I'm in exactly the right spot, kind of outside of the square, if I'm far enough away, I get, this is called Cantor dust. It kind of looks like the Sierpinski carpet, right? And it's actually a Cartesian product of two Cantor sets. And if I had an interactable, we could move the points as before, and we could see the Julia sets would change between all of them. But I didn't write that original code, and I'm not going to write this. Yeah.
If you're on the diagonals, does it also still look like a rectangle?
The diagonals. That's a good question. I don't remember. I think they largely don't matter. I think you like pass along the diagonal. And I think what happens is like your Cantor sets go from this direction to being this direction. I don't think anything crazy happens. Yeah.
What's the Batman logo on the lower right?
This is just supposed to be empty. It's supposed to be all red. But it's all done, like we computed these. And so these things converged at a different speed than these, or diverged at a different speed. It's an artifact of computation. Yeah.
What happens at 0, 0?
At 0, 0, you get, you're in the Mandelbrot set, so you get a rectangle, and the rectangle you get is a perfect square. So they're basically the same shape at that point. Oh, this is one of them. And again, it's actually a spread out Cantor set. A Cantor set is where you take an interval and you remove the middle third. And then for your subintervals, you again delete the middle third, and then you delete the middle third, and you delete the middle third, and you do that infinitely many times. And you end up with an uncountable number of points, but basically nothing's here. Right? It's just like scattering points that are nowhere near each other, and yet there's just a shit ton of them. This is the Cantor dust, which is, you can kind of tell it's a Cartesian product of Cantor sets. It's kind of neat. And the idea to compute these, by the way, is, again, you intersect the complex version of the Julia with the real line. You intersect the do it twice, actually, I guess. And there we go. So we intersect our old Julia sets with the real line. If our Julia set was connected, then what we're going to get, it turns out, is also connected. And we can show that the hyperbolic version is the Cartesian product of those things, those intersections. And so you have a product of a connected and a connected is a connected. In fact, you have a product of an interval with another interval, so it's a rectangle. Super boring. Or you have a product of an interval and a Cantor set, so you have a stretched out Cantor set. Or you have a product of a Cantor set and a Cantor set, so you get a Cantor dust. And so what you can do is you can do this analysis and you can show that the hyperbolic Julia set looks like a product of the intersection of the complex Julia sets with the real line. So that the only thing you need to figure out is what is the intersection of the complex Julia set and the real line. If you know that, then you know every point. Like analytically, you could calculate all these points. Okay, so you can do some manipulation, and it's just some change of variables. But you can end up with this equation. Anyone recognize this equation? There's a hint on the slide. It's okay if not. It's totally fine. This is called the logistic map. Question of logistics, it's fun. So this is the logistic map. It's incredibly important in dynamical systems. It's incredibly important in modeling in the life sciences. It's like one of the most basic differential equations that you end up running into. And what we conclude is through some analysis and change of variables, we end up finding that the R term here needs to be at least 4. So it turns out finding the Julia set that we care about is equivalent to understanding the logistic map for R greater than or equal to 4. And that would be fine, except that's beyond the scope of this talk, because the logistic map is the classic example of a chaotic system, especially when R is at least 4. So here, is a picture. If it looks crazy and chaotic, it's literally by definition. I mean, it is a chaotic system. And you'll notice that this is R equals 4 and everything has kind of, for lack of a better term, shit the bed. Like, this is called a cobweb diagram. They're super cool, but I just want you to look at this and be like, wow, that's really confusing. Yes, correct. So what you essentially can show through this analysis is that understanding these hyperbolic Julia sets, which come from this really boring Mandelbrot set, is equivalent to understanding the chaotic behavior of the first chaotic system that you would study in like a dynamical systems course. And that's the end. Questions, comments, heckles?
A random question. So,
Yeah.
with when you had those visualizations up of like the counter set cross, yeah, these.
Okay, yeah.
Is the circle in the middle just a remnant of
Yep.
just, okay.
Yep. Everything that looks weird is a remnant of computation. This is like 5-year-old MATLAB code.
Yeah.
Yeah.
You have an R2, one space where you have one axis the complex, one axis the real, and one axis the tau or the hyperbolic.
So we thought about this, and the answer should be no. Why was that? Okay, so let me stop. Yeah, of course you can. Sure. Why not? Right? You sure can. I don't know what anything looks like. I don't know how anything works, but I don't see any reason you couldn't do that. In fact, so there's other fractals where you take Cantor sets and you product them again. You get these Cantor cubes. But I don't know if you might need 2 hyperbolic dimensions for that. It's a great question. I don't know. You should examine it and then write a paper. Totally. Yeah.
There was a talk that I went to where they talked about, I think the title of the talk was like shining light through the measure sponge. And one of the results they presented was like that picture. If you try to shine light horizontally or vertically through that picture, it can't go through. So even though you just kind of have dust, there's no way of getting any light through with in the 2-dimensional picture. And then I guess with the sponge you are kind of restricted to like columns above like the like large openings.
Oh, but you can get light through a sponge, the 3D one? But like in certain directions?
Only through like the big holes basically.
Oh, well, that makes sense. Yeah.
And then they just had some kind of like, you can't get anything if you're trying to go like diagonal through, basically, which is like an analog to the 2D thing.
Exactly. That's awesome. That's super cool. I love all this stuff.
You mentioned MATLAB. What are the other kind of tools you use to make these like images?
Sorry. I mean, you can use whatever. You can use any sort of visualization software. What you would do, right? If you wanted to do this, is you would. How do you make these visuals? You plug in complex numbers. You iterate them over and over and over and over and over and over again in this polynomial you want. Check its size. If it's smaller than 2, after you've done 1,000 iterates, you call it good. And you color it blue. If it's not, color it red. If you want to be more subtle, you keep track of how long it took to fail, how long it took to escape, and then you color based on that gradient. And then you do that for 10,000 different complex numbers and you get an image. You go pixel by pixel. You let it run overnight. So it's not like a hard algorithm, it's just a slow, tedious algorithm. And it's not illustrative, it's just kind of.
How do you choose in which order you iterate the complex numbers you feed in this input?
So it's always just this on top of itself over and over. It's you pick your complex number, Z0, you plug it into F, and then you plug that into the function again. And you just do that, I don't know, 10,000 times, and then you check basically whether that's bigger or less than 2. That's your algorithm. And if it's less than 2, you call it blue. If it's bigger than 2, you call it red, and there you get a picture. Yeah, something worth trying. And so what do? You pick like, this is within some set of points that you care about, some complex numbers, and maybe the size of this thing is like 100,000 or something, and then you get the whole picture. And it just takes forever. Yeah. This is actually part of an RU we did, so we had a whole summer that we could let things run. Other questions, comments, heckles, jeckles? Yeah.
Maybe this is a silly one, but I mean, it takes that square shape, but how do you know that there's no possibility that there's another square somewhere out in the infinite of space?
That's a good question. And the answer is because, so the theorem says these are the 4 things that happen. And the way you know it is you read the paper, you read the proof. And we basically say, okay, assume, so there's only 4 conditions that you can have. You're either in the set, you're, one of your, you look at your complex as C, you break it into a CX and a CY, and you check, one of them should be within the rectangle and one shouldn't be. So that's something that could happen. They could both be outside of the rectangle, or I don't know, there's 4 options. There's literally 4 things that can happen, right? So you check all of them. It's not an exciting proof, which is why I didn't include it. But the paper's out there. You can go find the paper, read it. It's not hard, 6 pages long. Got a lot of pictures, really not a lot of math. Just enough to get through. Not a satisfying answer. But... Oh, well, no. Didn't end on a picture though. Someone else's picture. There we go. Sponge.
Other questions?
Yeah, so I mean, would it be reasonable to expect that if you you take the R join X and mod it by some other quadratic polynomial, that you'll get similar behavior, or maybe maybe what you get looks more horrible, but
yeah, in fact, yeah, but I have no idea what it would look like. We did think about things like this a little bit. I think we always ended up concluding that it was horrible enough that we didn't want to deal with it. Yeah. In particular, there's no way to get rid of 0 divisors. And in this case, the 0 divisors are exactly on the diagonal, which essentially means we can control them. We can see when they're coming up, we can be aware of them. If you modulo by something else, I guess if it's irreducible quadratic, you actually just get C back. If it's otherwise, you get some sort of twisted hyperbolic space where I think you are a linear transformation away from hyperbolic space would be my guess. And in that case, you watch what happens to your diagonals, and those become the new 0 divisors. So my totally off the hip guess is that if you're using a reducible quadratic, maybe square free quadratic, you quotient the exact same way, you would get a transformation of these. So maybe you'd have some curve or something if you had more of a curved 0 locus or something. Totally shooting from the hip here though. Not sure. You should look into it and then write a paper. In fact, you should talk to each other and write a paper. Fantastic. Yes. Happy to proofread it.
Cool. Just another round of applause.
How much more pizza?
Yeah, there's still plenty of pizza. I think it's full.
Yeah, whole pizza's full good.
Yeah. There is no QR code or anything of the sort this week, so don't worry about it.
No, I was here.
I'm just gonna make up numbers.
Yeah, the QR code.